Hello, this research project is entitled Smart Indicator Film from Butterfly Pea, Clitoria ternata extract for real-time assessment of cooking oil quality. I am absolutely thrilled to guide you through this today. We're going to be looking at a really innovative approach to a super common everyday problem: how on earth do we easily and accurately monitor the safety of the cooking oil we use in our food?
So here's our quick roadmap for today's explainer. 1. Introduction and problem statement. 2. Objectives and significance. 3. Research methodology. 4. Results and data analysis. And finally, 5. Conclusion and future studies.
All right, let's jump right into Section 1, Introduction and Problem Statement. First off, we need to establish exactly why this research is so critical right now. You see, cooking oil is everywhere. It's widely used in the food industry and, of course, in our own kitchens. But here's the catch. Repeated frying degrades cooking oil, and that poses some very real health risks to consumers. Currently, if you want to test for this degradation, you're looking at highly complex, time-consuming laboratory procedures. I'm talking about meticulously measuring the acid value and peroxide value. Honestly, these methods are just totally impractical for on-site use, whether you're in a busy fast food kitchen or just cooking dinner at home. So, what do the food industry and everyday households actually need? We need a simple, rapid, and eco-friendly real-time monitor. Ideally, we want a visual indicator, something that just changes color to tell you immediately, hey, your oil is safe, or nope, it's degraded, time to change it. And that brings us to the proposed solution, the butterfly pea flower, known scientifically as Clitoria ternata. This beautiful, vibrant flower is the absolute foundation of the proposed smart indicator film. It acts as an eco-friendly, biodegradable, and completely natural source material, stepping in to replace those harsh synthetic chemical indicators. Before we get into the heavy data, I just want you to keep this entirely natural starting point in the back of your mind. Moving right along to Section 2, Objectives and Significance.
The researchers laid out 3 very clear, distinct objectives for this study. First, they wanted to evaluate the film's colorimetric or, color-changing response to different pH solutions, covering both acidic and alkaline environments. Second, they needed to assess that exact same colorimetric response, but this time with the film placed directly into cooking oil that had been put through repeated frying cycles. And third, they set out to mathematically determine the correlation between the film's visual color changes and the actual measurable cooking oil quality parameters. Nailing these objectives is absolutely crucial because it establishes the foundation for sustainable, low-cost, smart food packaging down the line.
Next up is Section 3, Research Methodology.
So how did they actually pull this off? The experimental setup was incredibly systematic. Think of it like a highly precise scientific recipe. First up was the extraction of the butterfly pea flower, done at a 1:10 weight by volume ratio at 60 degrees Celsius for exactly 20 minutes. Next, the indicator film itself was meticulously prepared using a very specific formulation: 5% potato starch, 3% glycerol, and 15% of that butterfly pea extract. Then came the application tests. They tested the film across a wide pH range, going from pH 2 all the way up to pH 10. For the cooking oil test, they simulated typical household frying conditions. We're talking frying at 180 degrees Celsius for 7 minutes per cycle, and they tested the oil at 0, 1, 3, and 5 frying cycles. Finally, all the resulting data went through rigorous statistical analysis using SPSS.
All right, let's get into the really good stuff. Section 4, Results and Data Analysis.
What you're seeing here are the colorimetric parameters, L star, A star, and B star, as well as the total color difference, represented as delta E, across those various pH solutions. Looking objectively at the data, the L star value, which indicates the lightness, was significantly highest right at pH 6. But more importantly, check out the A star value. It decreased significantly as we moved from the acidic to the alkaline environments. This specific drop in the A star value is what gives us a clear red to green transition. Furthermore, the total color difference, that delta E, was greater than 6 across all the pH treatments. In plain English, that confirms these color changes are incredibly obvious to the naked eye.
And here is how that actually plays out in reality. Look at how the film's response shifts visibly from those really deep purples and blues in the acidic range, smoothly transitioning into striking greens and teals in the alkaline range from pH 8 to 10. These distinct visual color changes map perfectly to the L, A, and B parameters we were just talking about. So as a pure pH monitor, the film performs exceptionally well. But
What happens when we shift our focus to the cooking oil itself? Well, before we can test the film and the oil, we have to prove the oil is actually degrading. This data shows the physical-chemical parameters of the cooking oil at frying cycles 0, 1, 3, and 5. And the data doesn't lie. The acid value climbed from 0.74 to 1.05. The free fatty acid percentage went from 0.34 to 0.48. And the peroxide value? That saw a massive jump from 4.05 up to 11.23. These significant increases are all happening because of the hydrolysis of triglycerides and lipid oxidation during that repeated frying. The science confirms it. The oil is definitely deteriorating in quality. It's getting unhealthier with every single cycle.
So here is the million-dollar question. Does the smart film actually detect this deterioration? When we contrast the oil degradation data with the film's response when it's placed in that exact cooking oil across the same frying cycles, a pretty interesting pattern emerges. While statistically significant differences were technically detected in the color parameters, note the lack of a consistent colorimetric trend. As the frying cycles increased, the color changes just kind of fluctuated up and down. It didn't progressively reflect the oil's steady degradation like we hoped it would.
Once again, the visual evidence really highlights this reality. If you look at the film color before and after dipping it in the oil across cycles 0, 1, 3, and 5, well, unlike the vibrant, distinct shifts we just saw in the pH test, the film here exhibits incredibly limited sensitivity. There's just no clear, progressive visual change to warn a user that the cooking oil is going bad.
We can actually analyze the Spearman correlation data to mathematically prove this point. This data compares the colorimetric response directly to the oil quality. Delta E for pH showed strong, significant negative correlations with the oil metrics. For instance, we see a negative 0.742 correlation with acid value and free fatty acid. However, delta E for the oil showed weak, non-significant correlations with those exact same oil quality parameters, sitting all the way down at just negative 0.332. The math simply backs up what our eyes already saw. The film, at least in its current state, has a limited capability for directly monitoring cooking oil degradation.
Which brings us to our final part today, Section 5, Conclusion and Future Studies.
Let's summarize the key takeaways, clearly. The butterfly pea film is undeniably an excellent, visually striking monitor for pH levels. Furthermore, the study successfully confirmed the degradation of cooking oil through repeated frying cycles, seeing as acid value, free fatty acid, and peroxide value all increased exactly as expected. However, the film itself showed weak correlation and limited sensitivity when used directly in the cooking oil. And why is that? It's largely because cooking oil is a nonpolar system, which really impacts how the film interacts with it compared to those highly polar pH solutions.
And that leaves us with a provocative final thought on where we go from here. Future research absolutely must focus on evaluating the film in other nonpolar model systems. We need to expand the number of frying cycles tested, and most importantly, we need to deeply investigate the fundamental interaction mechanisms between the butterfly pea film and different polar and nonpolar solvents. Because unlocking that specific interaction, that is the key to finally bringing this awesome, eco-friendly innovation out of the lab and into our kitchens. Will the next generation of smart packaging finally be able to tell us exactly when our food is no longer safe to eat? I certainly hope so. Thank you for your attention. Have a nice day.